to Leticia Tarruell.
So, hello everyone. First of all, thanks Alexander for the introduction, and thank you very much for giving me the opportunity to present things that we do in my group here at ICFO. So I will be talking today about some pretty recent experiments, recent in the sense that they happened a bit before the lockdowns, but then we concluded them after we could come back to the labs this year. And so I will be talking about optically dressed Bose-Einstein condensates, and will show you how we can use this trick, optical dressing, to engineer a so-called chiral gauge theory. And I will show you how from images like these ones that you see in the background, and the fact that they are different, these ones and these ones, we can infer that we have made this chiral gauge theory in our experiment. So in my group, we study ultra-cold quantum gases. We study Bose-Einstein condensates for quantum simulation. So this is a typical picture of what we study in our lab. So it's a BEC of about 100,000 neutral atoms of potassium. And the goal of my talk today will be to make them behave as charged particles, these neutral atoms. And this is actually something which is kind of old in the field. Actually, after making BECs, people immediately went to set them into rotation. The idea then was to nucleate vortices to have a proof of superfluidity of the system. Because actually, when you just put BEC into rotation, if you go into the rotating frame, you can see that the Coriolis force is actually equivalent to the Lorentz force. So you can see your Bose-Einstein condensate as subjected to a magnetic field. And then you get beautiful arrays of vortices, and people could get the proof of superfluidity that they wanted. But actually, the physics of the system is in some aspects similar to type 2 superconductors. You get vortices as well. Now, you can then, in this configuration, in this rotating frame, make your BEC behave as if each atom is just charged and is subjected to a magnetic field. But you have other methods to emulate these gauge fields with Bose-Einstein condensates. One beautiful one is Floquet engineering. So this you can do if you put your atoms in an optical lattice and you shake around your lattice such that the effective time average Hamiltonian behaves as if there was a vector potential in there. So this is a field, this Floquet engineering, that is also quite old in our field. It was pioneered by the PISA group and then taken over beautifully by the Hamburg group. So this is one of the very first images from the Hamburg group where they could infer that they had engineered a vector potential here. And then afterwards, there were just more and more improvements on this technique. For example, beautiful experiments in Munich where one could use that to make magnetic fields, so realize the so-called Hofstadter Hamiltonian. So a lattice system subjected to a very strong magnetic field. But this is yet not the end. So there is another technique as well to make neutral atoms behave as charge. And this is so-called optical coupling or optical dressing, where you just induce transitions between internal states of an atom. And you can exploit that to also make atoms behave as if they were charged. And here in this experiment done by the group of Ian Spillman in JQI, who is really the pioneer of this method, what they did was a stripped system with 3 sites, let's say, that was subjected to a very strong magnetic field, like perpendicular to the plane. And then you get cyclotron orbits. But when you are at the edge of the system, the cyclotron orbits, they cannot close. So then you get skipping orbits. So the atoms just bounce off the wall, yeah, and keep doing like this. And they could beautifully see these skipping orbits, as you see here in the experiment. So one common thing of all these experiments is that these gauge fields that you engineer for your atoms, they are classical. So they really constitute a static background for the matter that you put in there. Yeah. So basically, you can think of these experiments in the following way. So you take your favorite technique. So it can be rotation, it can be shaking your lattice, it can be optical coupling, and you engineer a vector potential. And then if you time change this vector potential, you get electric fields. If you just change it in space, you can get magnetic fields. But basically, this vector potential or these gauge fields, they act on matter. Now, if we think in nature, normally we have also the opposite, that then the gauge fields change the matter, but then the matter back acts into the gauge field and also changes it again. So you have back action from matter. And the question is whether one can do that with quantum gases, find a way of engineering this. And you could wonder, I mean, why would I want that? Okay, the long-term goal is you want to simulate gauge theories. I mean, that's what you have in nature. You have these gauge fields that are quantum and that's coupled to matter in a given way. And you want to simulate these gauge theories because they are the fundamental description of interactions between elementary particles. That's a high energy physics perspective. So if you could do quantum simulation of these, that would be cool. Yeah? And also because these gauge theories, they come many times as very powerful, effective descriptions of strongly correlated systems, like the ones you find in condensed matter physics. So you could think of not engineering in your lab the strongly correlated system, but directly the gauge theory, and you would also learn from this. Yeah? So this is a really long-term goal in the field, and a lot of theories have been wishing for that for really, really long. So there are really many theory papers on this topic. And if you want to have an overview, I recommend you to have a look at this review paper that really lists them and discusses them in quite some detail. And basically, at the end, what you want is to make this vector potential A that I wrote here, some quantum dynamical quantity, an operator that couples to matter and that fulfills some specific local symmetry constraints such that it makes a gauge theory. So let me explain these three things that I said in a bit more detail. And for that, I think it's nice to take a gauge theory that maybe we all have in mind. So for example, one of the gauge theories in high energy physics, but I would take QED because this one we are a bit more familiar than QCD, I would say. Yeah. So then in QED, what you have is that gauge fields are quantum mechanical entities and they are dynamical. Like they have propagating solutions even when there is no matter. You think in electromagnetism, you have photons and the photons, they propagate even in vacuum. Yeah. So if you want to emulate these with quantum gases, you will have to use particles in principle that make matter and particles that make the gauge field. So a priori, it's complicated because you would need two species. Yeah. Then these matter particles and gauge particles, they need to couple in a particular way. And on top of that, they need to fulfill a local gauge symmetry. And if you think of the QED case, I mean, it's pretty clear that in every point of space, you need to fulfill Gauss law, for example. Yeah? So these, in any quantum simulation, you need to also ensure. And that makes the thing pretty tricky to do in the lab. I mean, these three requirements here. So let me tell you from an experimentalist perspective what has been done. So there is actually a lot of progress despite the fact that this is a hard problem. So several experiments have looked at engineering building blocks for making these lattice gauge theories in the lab. So basically making that in very small systems. For example, here, that's the Pan group in Heidelberg a few years ago on a plaquette. They could engineer some plaquette interactions, or more recently in Munich, Z2 lattice gauge theory, well, just on a level of a double well. Yeah, so the building block of that. And then also more recently in Heidelberg, the building block for a U1 gauge theory was engineered. Yeah. So this is very nice because it really fulfills all these criteria, but it's on the level of just one side, two sides, four sides. Can you go beyond? I mean, the ion people did, actually. They did something really smart. So they wanted to simulate an extended 1D gauge theory, so-called Schwinger model. And what they did is that instead of simulating gauge and matter, they eliminated the gauge field using the local symmetry constraint. And then they get a model only for matter, which you would say it's easier to make in the lab. There is a price to pay because by doing that, you really get funky interactions for the matter. So for them, they got long-range interactions for the ions, but this is something that they could actually implement, and they have done it beautifully in this first paper in 2016, and also more recently using some variational quantum simulation tricks. And another system that actually makes this type of extended 1D gauge theories, but where you eliminate the gauge field, are Rydberg chains. So this is the experiment in Harvard, where they saw some really weird dynamics in a 1D system, these scars and so on. And then it was understood last year that actually this can be seen as a realization of a gauge theory. Yeah? Where again, I mean, you have eliminated this gauge field, and then you get weird interactions and weird things happening for the matter. But even further, I mean, over the last year also, there was this beautiful experiment in Heidelberg in the PAN group, where they could indeed make a 1D gauge theory, and where they could keep matter on the gauge field. So this is really, I think, the furthest experiment in this direction in the field. Now, these gauge theories, we took the example of QED to understand basically what the requirements were to make them in the lab. But they don't appear only in high energy physics. They also appear, as I said at the very beginning, as effective theories for many condensed matter systems. For example, in two-dimensional systems, spin ice or spin liquids, they are described by effective gauge theories very similar to those. Yeah? Now, if you go to the condensed matter world, actually you can get other types of gauge theories. You can get so-called topological gauge theories. This is, for example, the type of gauge theory that effectively describes fractional quantum Hall states. And there you have gauge fields, but they don't have their own dynamics. Their dynamics is locked to matter, or in other terms, these gauge fields, they don't have propagating solutions. So they will have dynamics, but in the sense that when matter changes, this gauge field changes. And this you can understand a bit like if it was a photon that was very, very massive and then cannot propagate anymore. Yeah? Or in other terms, this is a topological theory. So then you cannot have small perturbations of the vacuum. That would be like the propagating waves, like the photon propagating. So that's why this photon is very, very heavy. Yeah? But this, maybe I will explain a little bit more what I mean by that, but giving you the example of a fractional quantum Hall state, that's where such theories are best seen. So then you have a system of electrons in there subjected to a very strong magnetic field. And then we know that this system is very rich, has interesting things happening because its excitation, so quasi-particles, they have the funny property that when you exchange them, you get a statistical phase, which is not 0 or pi, yeah, when you exchange two of these quasi-particles, but can be anything in between. So they are anyons, yeah, for any phase. And now this is a very complicated to describe system, but people came up with the idea that you could make a simpler description if you think that this system you can also view as non-interacting electrons, but that would be coupled to a magnetic field, but an effective one that the system makes by itself, which I represent here with these solenoids around here. And now there would be flux attachment, it's called. So like a mechanism with which each electron would capture one of these flux tubes and form a composite. And now these composites, if you exchange them, then you see that you can get a different phase from 0 or pi. Yeah, so no bosons, no fermions, because you have the Aharonov bomb effect. So basically you have the Aharonov bomb phases when you exchange them, and this can give you a different value in here. And by the way, in this composite particle picture, you can also see that these anyons, they can have, I mean, these quasi-particles in these systems, these composite objects, they can have fractionalization of charge in the spirit of what Emmanuel was presenting in his talk yesterday. So actually, what is this magnetic field that the system, I said, self-generates and takes the form like this quanta of these flux tubes? So this is a magnetic field that needs to be proportional to the density of matter because each particle attached to one of those, yeah, and it's so-called a Chern-Simons field, and it's called a Chern-Simons field because it's actually exactly the local symmetry constraint of a particular gauge theory, which is the Chern-Simons gauge theory. So actually, this system, effective system that I describe here, that would describe the physics of the 2D fractional quantum Hall state, is just described by a gauge theory, this Chern-Simons field coupled to matter. And now what we wonder is whether with quantum gases, instead of maybe simulating the strongly correlated system that might be hard to do in the lab, can we just directly simulate this effective gauge theory and learn physics from that? Okay, so then if you want to do that, what are the requirements? It's maybe a bit less challenging than to have gauge particles, matter particles, but there are still quite some tricky things to sort out. You need to make a density-dependent gauge field, like this Chern-Simons field that was proportional to density before. You need to have matter gauge field coupling, and you need to enforce this local gauge symmetry. So I told you before, the fact that this magnetic field needed to be proportional to the density of matter, that was the local gauge symmetry for the Chern-Simons gauge theory. Yeah? So that's a bit like the Gauss law, but for this particular gauge theory. And then what is the status of experiments for just fulfilling all these requirements at once? So people have managed to do building blocks, so engineer some density-dependent Pyre phases in lattice systems, either with two-component fermions in Zurich or with Rydberg atoms in Paris, or even in the group of Chengqing in Chicago to do some density-dependent Pyre phases, so some vector potential at the end that depends on n in the lattice. But they did not implement the local gauge symmetry. So these things are really nice. They are a step forward to what we want to achieve, but they don't make the full gauge theory. And then the question is whether we can do that. And doing the 2D Chern-Simons model that I told you before, this is pretty hard. So we are not yet there. But what I will show you is how we can do a one-dimensional version of it. So a simpler model, which is a topological gauge theory. So let me maybe tell you a bit more what we exactly do. So we do a model, which is what you get if you take this 2D Chern-Simons theory with the anions and so on. And now you reduce it from 2 dimensions to 1 dimension. So you just set the dimension to 0. So you just get a line. Yeah? And then when you do that, instead of having this magnetic field that is proportional to the density of matter, what you get is a vector potential that is proportional to the density of matter. This model was proposed quite some years ago, actually, as a method of trying a toy model for getting anions not in 2 dimensions, but in a 1-dimensional system. And then it was studied intensively by Roman Jakiv and collaborators. And they realized that actually it's not a good model for these linear anions, which was the initial goal, but it has some really weird excitations, these so-called chiral solitons, that basically tell you that if you have a wave packet that moves in one direction, then it will spread when it moves in one direction, but it will remain cell-bound, like forming a soliton, a matter soliton, when it moves in the other one. And what these people studied also is in detail the relation of Chern-Simons and the 1D BF theory. And they also showed that actually the fact that the vector potential is proportional to density allows you to eliminate this gauge field and stay only with the matter, yeah, because you can just replace this local symmetry constraint into all your equations. And then that's essentially the trick that was used for the ions that I told before. But then you get equations for the matter field that have something weird happening there. So you have an interaction term that is a bit strange because it has this nonlinear current form. So you have here the current operator times the density, instead of having like density square as we are used for contact interactions. And actually you can understand what this term means if you look at an atomic wave packet, for example. So then the current operator is the velocity times the density. So velocity is momentum over mass. Yeah. So when you replace that, you get that this system has chiral interactions. That means that the interaction part of the Hamiltonian has this form. So it has an n square term, as we are used to for contact interactions, but it's multiplied by momentum. So that's telling you that interactions change their magnitude depending on your momentum. Depending also on the sign of the momentum, they can change sign. Yeah? And that tells you that this is a strange system because this is a system that explicitly does not have Galilean invariance on the interaction term. Yeah? And this is exactly the model that we will look at in the lab. So with this, I finish my introduction, and I don't know if there are questions. Maybe here that's a good moment for questions, because otherwise I will move on.
So far, we don't have questions, but maybe I can ask something. So do you have, and so can you manage to change experimentally this momentum in this chiral interaction? So can you access this momentum?
Yes, so this I will show you exactly in a minute how we can make clouds with different momenta, center of mass momenta, and also their spread, and how we can see interactions changing there.
Sure.
So should I go on then? Okay, so then
Yes.
with this I come basically to the outline of my talk, what I really want to show of what we do experimentally. First, I will show you how we engineer this chiral BF theory, this 1D gauge topological gauge theory using optical dressing, and then how we probe these chiral interactions in an optical waveguide, observe these chiral solitons, and see this BF gauge potential. So let me start by how we make things work. So what we use is optical dressing to create these artificial gauge fields. And this is actually well-known stuff, but let me go through it first, because otherwise we cannot understand the novelty that I will present you in a minute. So basically, we take a Bose-Einstein condensate, we subject it to two counter-propagating laser beams that have cross polarizations and that just link two internal states of the atom, this spin up blue state and this spin down green state, through a two-photon Raman transition. And now in this system, what you have is that when atoms are in one of the states, to change to the other one, they need to absorb and re-emit a photon. So they just get a momentum kick of 2 times the momentum of each of the Raman beams. So you can see this system as like the dispersion relation of each of the atoms. They are shifted by this 2kr, which is the amount of momentum that you get when you go from one to the other. And actually this kr is a single photon Raman kick with Raman momentum that you see defined here. And I will, from now on, set these to 1. So I will always work, write the momentum in terms of kr. Yeah? And then the associated energy is the recoil energy, which I define here. So now when I introduce this coupling, what happens is that these bare states of the atoms, they get modified by the light field. And actually we have an avoided crossing that happens here. And we get some new dress states that I have written here in detail. So the lower dress state here minus and the upper dress state plus, which are combinations of spin down and spin up with some weights that depend on momentum. Now, this is what happens for small Rabi coupling, where you still see the memory basically of the two parabolas that I started with. But when I make omega large enough, then I get a dispersion that becomes parabolic. Yeah? So that looks like a new particle that just has a spin composition that changes with momentum. Yeah, and we focus in the following in this lowest stress state, the minus state, which I have written here, and you see that the spin composition when I change momentum changes. So if I'm at positive large kx, then I'm mostly in the green state, and when I'm here, I'm mostly in the blue state. Yeah? And then when omega is much larger than 4 times the recoil, then in the so-called adiabatic approximation, this particle is very much like a normal particle. It has a parabolic dispersion and so on and so forth. So things become more interesting if we introduce some detuning between the two beams, because when we do that, then depending on the value of the detuning, then we would have this parabolic dispersion in the lowest stress state that either shifts to the left here, no? Or to the right. And close to this minimum, this system then we can see as if it was subjected to a vector potential, A naught, which has a magnitude which is proportional to this detuning, this 2-photon detuning delta 0, and which is static. So that's how you engineer actually vector potentials with this optical coupling. No? But this is a fully static vector potential, so it's really a classical gauge field. Now, if we want to make it density dependent, yeah, and we want to give it some dynamics, then what we need to do is to introduce interactions between the particles, which I've done here. And we cannot use any interactions. Actually, what we need to do is that we need to give take a system where the two states, the up and the down state, they have different coupling constants. So one interacts much more than the other one. Because when we do that, then because of mean field shifts, then there is a differential mean field shift of the two states. One gets little shifted, the other more when we put many particles. And then the detuning of this Raman process becomes density dependent. So we have a density dependent detuning that depends on the difference between the coupling constants and the density of the gas. And that means that because the vector potential now is proportional to the detuning, then we will have a density dependent vector potential, which is proportional to n. This is a result that was proposed quite some years ago theoretically by the group of Patrick Oberg. And they also showed that the Hamiltonian that describes a system, Bose-Einstein condensate subjected to such density dependent vector potential, has this form where you basically have matter minimally coupled to a density dependent vector potential. And you see this equation I wrote just without hats in the fields and so on and so forth, because this is a result that is valid at the mean field level. Yeah? One thing that you also realize when you're an experimentalist and you read this theoretical proposal in detail is that the result that they derive is only valid for very large values of the Rabi coupling in this so-called adiabatic limit. And when you put numbers, you realize that, yeah, that sounds very nice, but if I try to do it in my lab, it's really experimentally unrealistic because I need such large power for my Raman beams that I will also have a lot of photon scattering and my system will live super, super shortly. So I would not have time to measure anything on that. But I think that's why this proposal remained unexplored for a really long time. But if you think a bit further, then you realize that, I mean, how can it be that at the very large coupling limit, I get this nice model? I mean, physics needs to be continuous. So what happens if I reduce my Rabi coupling? Can't I just recover something similar to this Hamiltonian, but in a regime where I can measure? So that motivated us to look further at this system and to try to derive this PF theory from a different point of view, like derive it microscopically. So basically what we do is that we set Rabi coupling, which is large enough. Actually, this Rabi coupling sets the gap between these two dress states. And it needs to be large enough that we can actually forget about the higher one and focus only in the lowest one. And we know that no energy scales in our system can couple us to there. And then we can compute what are the effective interactions for atoms in this dress state here when we just trace out the upper one. And this is something that we studied not in the presence of optical coupling, but of simpler radio frequency coupling before the lockdown in my group. And what we saw is that effective interactions depend on the dress state composition. And that's kind of obvious. Like if you are mostly in the up state, then you scatter like the up atoms. If you are mostly in the down state, then you interact mostly as the down atoms. And then if you are in a combination of the two, then you have interactions that are kind of average between what you would have in each. And thing new that comes when you have optical coupling is that this dress state composition is momentum dependent. So then these effective interactions will become momentum dependent. So here for positive large momenta, you will interact mostly like the green atoms and here mostly like the blue atoms. So your interactions can change if you are changing around here. No? And actually we can formalize these by just taking some momentum and then writing the effective interaction term in the Hamiltonian truncated to this lowest dress state and do a series expansion of it in a parameter Q, which is small because this is the difference of the momenta that we explore compared to the momenta where we do the expansion. And this needs to be small in Raman units, basically compared to the Raman momenta and the Rabi frequency. Yeah? And if you put yourself in the right conditions, this is a small parameter, and then you can show that interactions are chiral. So you can restrict yourself to the first term in the series expansion, and you find that the effective interactions of your atoms become proportional to Kx, to the momentum along the Raman coupled direction. And then if you do that, that's exactly the ingredient that you wanted to make this PF theory. So actually exactly for 2-photon Raman detuning 0, you can show that you exactly realize the BF theory at the quantum level. So it's really the same equation as before, but now I have put hat operators in all these quantities because it's not just limited to mean field. I mean, you keep all quantum fluctuations and so on and so forth. So we are still minimally coupled to density-dependent vector potential, which is now an operator. And there is a price to pay. The price to pay is kind of small because it's just that instead of putting the mass of the particles, we need to put an effective mass that depends on the Rabi frequency of the Raman coupling. Yeah. This is the result that you get for delta 0 equals 0. Actually, this result you can even generalize, so you can preserve this minimal coupling for other detunings, provided you look at the right momenta. Yeah? So provided you have this relation between momenta and detuning, then things work well. And also for things to work well, you need to have this parameter that is small, so you need to have a reasonably large Rabi coupling. But then when you're an experimentalist, you get particularly happy because you realize that this result is valid way beyond the adiabatic approximation. So it becomes valid for experimentally accessible values of omega. So that's something you can do in the lab. So with this, I come to show you how we do this experiment. So how do we make these chiral interactions in practice and probe them? So these are experiments that we do on our potassium machine at ICFO. So this potassium machine produces Bose-Einstein condensates of the different potassium isotopes, so potassium 41 and potassium 39. But for this experiment, we use potassium 39 because potassium 39 has nice flashback resonances that allow us to tune the interactions, and in particular, to make them chiral. And in particular, we use these two spin states, spin up, spin down, are 1, 0 and 1, 1, at magnetic fields on the order of 385 Gauss, where the scattering length is such that for the down state, it's large and tunable and positive. Yeah, you see, depending on magnetic field, we can change its value. For the up state, that's the blue state, it's actually very small, and it can be positive or negative, depending on the exact magnetic field that we choose. And then for the interactions between the ups and the downs is a bit negative, but it's actually pretty small. And then the experiment, you cannot see much in this picture, so let me show you here. So we have the Bose-Einstein condensate subjected to counterpropagating Raman beams. The atoms are restricted to a 1D dynamics, basically, by putting an optical waveguide here, and then we image them in situ with a high NA lens. We set magnetic fields with these bitter electromagnets, and in all experiments, we basically at t equals 0, remove the trapping potential and just look at the dynamics on this waveguide subjected to these Raman beams. And now to come to Daniel's question, so how do we do to prepare different momenta? Actually, we add another couple of laser beams, these black beams that I put here, with which we do Bragg transition, so 2-photon transition to give momenta to the atoms. And then by doing that, then we can, for example, give them positive momenta or negative momenta and see what happens. So that's what we do here. So we have our atoms. We kick them with this Bragg beam to the right here. And then at that time, we also remove any trapping along the direction of the waveguide. So they will be able to move unrestricted in the waveguide and subjected to the Raman beams. Yeah? And what you see is that when we kick them to the right, the atoms, they start to expand. And that makes sense because we remove the confinement along the waveguide, so they just spread. But if we do exactly the same experiment, but we kick them to the left, yeah, then what we see is that they propagate along the waveguide without any dispersion. So the size is not changing over time. And this actually is immediately telling you that your interactions are chiral, because if you look, the effective interactions of your system that you can compute with our model, when you kick them to the right, they turn out to be positive. So that's why the BC is expanding. But when we kick them to the left, they turn out to be negative. So they are attractive. And that's what keeps the shape of this cloud. Yeah? And we can formalize it just by seeing what's the longitudinal size versus time. And we see on the kick right, we see this quick expansion. On the quick left, we see this size changing. So the fact that these two directions are behaving so differently is telling us that the system is chiral. And also the fact that this size is not changing over time is telling us that we form a bright soliton. So basically a self-bound state where atoms are held together because they have attractive interactions, but they don't collapse because there is quantum pressure, yeah, that is repulsive and compensates for that. So the two terms just balance the attraction and the repulsion, and then they form something self-bound that can keep the same shape over time. Yeah, it's a solid. So now, can we have a better look at this chiral soliton? So how do we see that this is really a soliton and that this is chiral? So we just take our atoms, we kick them left, and then we let them evolve. That's what I showed you before. But we just don't let them evolve freely, because after some propagation, we just build a wall for them. And this wall, in the lab, of course, it's not a wall, it's a repulsive laser beam that we focus away from the atoms here on this left side. And then when we do the experiment in the presence of the wall, we see the following. So the atoms are here, they are self-bound, propagating like a soliton happily until they reach the wall. When they reach the wall, they compress a little bit, and then they just bounce off. And this, of course, it's true if you make your wall high enough. So we make this barrier so high that the atoms cannot tunnel through it. No? So it's much higher than their kinetic energy. And then what we see is that after reflection from the wall, the atoms are not self-bound anymore. They start to expand. No? So it is a bit like if we had a particle, this soliton is like a big particle that exists. And when it reflects off the wall, it disappears, it dissociates. This is what you are seeing here. So we have solitons when we move in one direction, but they disappear when we go in the other. So you could think, okay, but maybe your barrier is doing something strange, and that's what's dissociating the soliton. So we also thought that, and we did this sanity check. So basically, we made a soliton with a single component BEC in the down state, where we can set interactions to be attractive at the nearby magnetic field. So here we set these interactions to be -2A0. Here, for example, for this optically dressed BEC, we have -3A0. So this is all very similar. And you see that this chiral soliton only exists when propagating left, and then it disappears. But for a standard soliton, it does not care. Yeah, when it comes to the barrier, it compresses a little bit, but then it bounces off and it happily keeps existing afterwards. Yeah? So then here you can look at what happens in the sizes, and you see the standard soliton, okay, compresses a bit when coming to the barrier, but then stays like this, and the chiral soliton starts to expand. So this is telling you that the soliton we make, it really only exists here, only when moving in one direction. Now, I told you this chiral BF theory, people, when they studied it theoretically, they saw one of the main manifestations is that there are these chiral solitons for the matter field. So these self-bound wave packets that exist only when you move in one direction, not in the other. So how are we standing with respect to the predictions of the chiral BF theory? So our experiment with the Raman couple BEC, is it described by this BF theory? So this depends on this expansion parameter that we use to derive the theory in our conditions, this Q that I defined before. And then what I show here, the blue points are the data for the left propagating clouds. And you see that for this experiment, the value of Q is actually very small. And actually, we are very well described by this BF theory. When we do the bouncing, we have the first points until we reach the barrier, we have small momenta, then we are described by BF theory. Then when we bounce off the wall, we acquire very, very large momenta. And then we go out of the validity of this theory. But phenomenologically, at the end, everything remains the same. And if when we kick right, we have very large momenta. So this approximation that we have small momenta is not true. But that does not mean that we don't understand our system. Actually, these lines here are our theoretical expectations. This is what you get from our effective interaction model restricted to the lowest dress state, and so on and so forth. And what happens is that the Hamiltonian that describes our system is like the BF theory with some additional terms that break the gauge symmetry. But for all the regime where we do these solitons, we are described by this BF theory. So what we are seeing are these chiral BF theory solitons. So with this, I really come to the last part of my talk. where I want to show you how we can not only observe these chiral solitons, which are one of the manifestations of this BF theory, but also reveal this BF gauge potential. Because, I mean, all the story was about making a density-dependent vector potential that then is the key ingredient for a gauge theory. But for the moment, I only showed you what happens with matter. So how can we observe this BF gauge potential A of n? And you see, I mean, this is a vector potential. So in principle, a vector potential is not something you can observe. No? But what you can observe are variations of it. So what we look at are at time variations of this vector potential, which result in an electric field, which will be a density-dependent electric field, which actually, because this vector potential is proportional to density, are proportional to time variations of the density of the system. Yeah. So if we just time variate the density of the system, then we will change the vector potential in time. So we will get an electric field. So we will really see back action of matter into this electric field. So how do we do this time variation of the vector potential? Well, we change A of n by changing the density of the cloud very much by expanding it. So we just prepare our Raman dress system. Actually, now we don't kick it anymore, just prepare it. And at t equals 0, we remove the trap in the longitudinal direction. So we let it expand with the waveguide on and with the Raman beams on. And this is what we see. And what we see is that initially the cloud, it's just symmetrical, but over time it starts to acquire a more and more strange shape. So it's becoming asymmetric. And why is this happening? Actually, you can understand this microscopically pretty well because you have a wave packet where atoms are in a superposition of these up and down states. But now when you let it expand, we know that for some momenta, the atoms will be in one state, and for the other momenta, they will be in the other state. And now these two states have different interactions. So microscopically, the atoms in the state which interacts less, they will just expand less. Yeah? Whereas the atoms in the state that interacts more, they will have more interaction energy, so they will expand more. No? And this over time will make your clouds asymmetric, very much like what we see here. But if you look at this microscopic picture, you don't really see the link with this BF gauge potential and this density-dependent electric field. Actually, you can also interpret what is happening in your data like this. So basically, you have your wave packet here, and now when the density changes over time, then you will induce an electric field, and this electric field will depend on density because this density drop will be different in different parts of the cloud. So it will be such that you get an electric field in this direction for the peak, and electric field in the opposite direction for the edges, and also these two would be of different magnitudes. So you will get a distribution of different electric forces over the cloud, and that will skew your distribution and distort the cloud, making it asymmetric. So this is all hand-wavy, but we can compute things within this effective BF theory. This is what you get here for parameters that are not too far from those of the experiment. So we have initially the symmetric cloud, and now at t equals 0, we let it expand, and then we start to get these electric forces that, as I told you, are different on different parts of the cloud. And this distribution of forces just skews your wave packet, and the solid line is what the BF theory predicts, and the dashed line is what full GP simulation of your Raman coupled system predicts. And you see they are in good agreement. So the system is well described by this BF theory. And you also say that it's asymmetric, really becoming asymmetric. Here, the gray line would be what you expect for a symmetric cloud. So now let's have a better look at the experiment and analyze this data better. So this is what I've put here. So what I plot here is the skewness parameters. So third central moment of the distribution divided by second moment cube, which is a good measure of the asymmetry of a distribution. And you see that over time we have skewness increasing. Now, this is what we get for a set of Raman coupling parameters. We can change those parameters. And this was something we had initially not really thought of doing, but then we were in the lab and then tried. And then we were initially very surprised because for some parameters, we can get skewness fully disappearing. And for others, it's different. It goes first negative, then positive, and so on and so forth. So initially, we were very puzzled by that. This is what happens when you change detuning in your system. But then we realized that this is also something that we can understand very well. And it comes from the fact that we have not so large Rabi frequency. Because everything that I told you about the asymmetry of the distribution in the previous slides was about the interaction part of the Hamiltonian. This electric field basically comes from interactions. But then there is also the kinetic part of the Hamiltonian. And this kinetic part, because we don't have so large Rabi coupling, is such that the dispersion relation of the atoms is not really parabolic. Yeah? So actually, you get some effective mass for the atoms that depends on momentum. And this dependence on momentum of the effective mass for positive detuning tends to make your cloud asymmetric in the opposite direction as the electric force. So these two effects cancel out. That's why this data set is kind of not showing any asymmetry. For negative detuning, the two effects are reinforcing. And the good thing to look at is zero detuning, because then these kinetic effects are canceling out, and then we only see the electric field. And actually, these effective mass effects are what make that the mapping to the BF theory otherwise breaks down. So actually, this is exactly also a regime where we realize this BF gauge theory. And in this regime, the fact that we see asymmetry here, you see, is a manifestation of the back action between matter and gauge field, which we wanted to see. And with this, I really come to the conclusion of my talk. So I showed you a scheme for making this chiral BF theory. That is a theory that has a density-dependent vector potential, which is equivalent to having chiral interactions in a BEC, and which is a 1D gauge theory, a topological gauge theory, which is a dimensional reduction of the 2D Chern-Simons theory. And I showed you how we realize it in practice by combining Raman coupling and a system with tunable interactions. And then I discussed experiments where we show its two main manifestations, the formation of chiral solitons and the back action of matter into the gauge field. And then we are now thinking of pushing these experiments further to look at more properties of this gauge theory. So one thing is to look at this system and try to see an equivalence of this with the edges of a fractional quantum Hall system, which is what the model was built for, basically, to generalize these two systems with stronger interactions, to try to see linear anion models. And I think what we would all like to see is the extension of this to 2-dimension, for which there is a proposal, which is something we could do in our experiment if instead of using counter-propagating Raman beams, we would use Raman beams with orbital angular momentum. And with this, I really come to the most important slide. So the people that did the work. So this is my group in Barcelona. And all these experiments I presented today are done by the potassium lab. So the people in red. So the people in blue, they work on the strontium experiment that we are building. And some of you maybe saw Jonathan's lab tour yesterday. So Jonathan, Sandra, Roger, Vasily are working on this lab. And on the potassium lab, the experiments on the BF theory were done by these two smart PhDs, very smart PhD students, Craig and Annika, and two postdocs, Letra and Ramon. And also there were important contributions at the early stage of the experiment of two former PhD students of the group, Cesar, that is now in Munich, so probably many people also from Munich know him, and Julio, that is now working on the QTech industry. And for making all this mapping of our experiment to the BF theory and also navigating all this gauge theory business, we had huge support from Alessio Celli from UAB, and also from many theory friends in Edinburgh, in Barcelona, in Hanover, in Vilnius, in Trieste, that really explain us a lot of things. So with this, I want to thank you very much for your attention, and I will be happy to answer questions.